Hello and welcome back. We are very glad to see you, and big thanks to all of you who have subscribed to our channel since our last video. In today's video we will take a slight detour to another popular genre of YouTube videos, reaction and debunking, instead of our usual electronics tutorials. So, let's get straight to business at hand. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. No matter if you are new to the world of electronics, or just trying to broaden your knowledge, learning about transistors and amplifiers is one of the pillars of modern electronics. In higher education, there are whole semesters dedicated to this topic, and many make transistors their life's calling and professional choice. So, no wonder there are so many books, tutorials and videos about this subject. However, if you try to learn about transistors in general, and amplifiers in particular, you might find yourselves lost in ambiguities and sheer volume of unnecessary fluff, following every tutorial and video clip. At the end, most likely you will find yourselves knowing even less, and being more confused than you were before you started to learn about transistors and amplifiers in this way. Simple Google search, ignoring the AI slop and hallucination, will produce page after page of schematics and links to tutorials and video clips. All of them dedicated to confuse the hell out of you and make transistors and amplifiers as impossible to understand as they could. In higher education, some of the students even drop out when faced with couple of semesters of this gobbledygook. Transistors and amplifiers seem impossible to understand. It is truly misunderstandable how a simple electronic circuit made of transistor, battery, for resistors and a capacitor, can lead to such complications. Why does this simple schematic require semesters of higher education, thousands upon thousands of pages of tutorials, countless hours of video clips, all of them unsuccessfully trying to explain how to choose and put 7 components in correct formation? And let's remind ourselves that transistor is nothing more than overglorified current-controlled variable resistor. Nothing more, nothing less. You watching this video guarantees that you are 99% good person, and remaining 1% depends if you have ever made a biggest mistake of your life, asking a professional to quickly explain transistors and amplifiers to you. The conversation goes something like this.
I would like to build an amplifier. Great. Do you want to build current, voltage, or power amplifier? I don't know. I have this and I want this. In my 17 billion years of experience, and as twice as many amplifiers built, I've never known someone who doesn't know difference between current, voltage, and power amplifier. Can you please explain difference to me? You are stupid if you don't know the difference. It took me 18 billion years of experience and is 4 times as many amplifiers built. And I'm a professional. You will never learn this. Give up.
We ourselves have had this exact conversation too many times, and each next conversation was as uncomfortable and demeaning as any previous one. It seemed to us that amplifiers are something beyond our reach and understanding. Forever. So, next best thing, beside turning to agriculture, was to try to learn about transistors and amplifiers online. First suggested page on Google search spewed this schematic and following tutorial that we are about to react to and debunk, as one of the worst tutorials, and as one of the worst explanation of amplifiers ever. And competition was fierce. Between professionals with as twice as billion years of experience than universe is old, Ivy League college tutorials and professors, being all professorial and serious, exotic dialects, fingernails of all sizes and shapes, and schematics chiseled on cow hide, this bovine sophistry takes rightful first place as worst tutorial ever. It all starts with simple schematics of common emitter amplifier, as one displayed on the screen. The author chooses 30 volts for power source. Little bit unusual, but we can assume that author wanted to maximize output signal, so he chose maximum power supply allowed for common NPN transistor. In our previous videos we have covered maximum ratings parameters for common NPN transistor and learned that maximum power supply is 40 volts. Also, we have learned that best practice is always to go with half of recommended maximum value for reasons of heat dissipation, stability, and longevity of the component. So, 30 volts is a little bit pushing it, but nothing unusual, especially if we want to maximize our output. So far, so good. Next, out of the blue, the author decides that current running through emitter resistor will be exactly 11 milliamperes. In addition to that, the author also decides that voltage drop across emitter resistor will be 10% of power supply. So, without any explanation given, we have 11 milliamperes of current running through emitter resistor, and voltage drop across resistor is decided to be 3 volts. Choosing 10% for voltage drop across emitter resistor and arbitrary current is supposed to be standard practice, as you have to start from somewhere. This is first out of many red flags that this tutorial raises. First of all, where does all these arbitrary values come from, without any explanation? Where is the logic in choosing random current, when you are trying to build voltage amplifier? The current running through collector, and consequently emitter should be last of your concerns. If your logic was to maximize output, why not choose higher amperage? According to datasheet parameters, you can go as high as 200 milliamperes, even half of that would be enough to give you decent power to drive output load, audio speaker for example. And why such big arbitrary voltage drop across resistor emitter? This immediately implies that voltage drop across resistor R2 will have to be the same as combined voltage drop of base emitter junction added with voltage drop across emitter resistor. These 2 points have to be at same potential difference, or laws of electronics fly out of the window. Next, the author arbitrarily chooses half of supply voltage as middle point around which amplified signal will swing in output DC domain. In this case this is 15 volts. This implies that voltage drop across collector resistor has to be 15 volts as well. This should ensure that output signal has entire 30 volts DC domain to swing in. But, what author of this travesty deliberately chooses to ignore is that there is voltage drop across base emitter terminal, alongside voltage drop across emitter resistor, so entirety of 30 volts of DC domain provided by power supply is not at disposal for our AC amplified signal to swing in. This deliberate omission introduces one of the most elusive errors in amplifiers design, clipping of the bottom of amplified output signal. Middle point should be calculated taking into account voltage drops across base emitter junction and across emitter resistor. If we correctly calculate DC domain available at our disposal, we get value of 26.3 volts available. Now, half of that is 13 volts. But this new middle point has to be offset by the sum of previously mentioned voltage drops. So, our new correctly calculated middle point stands at exactly 16.7 volts, instead of erroneous 15 volts. Now, let's get back to the tutorial. This approach is often referred to as dealing with right-hand side of the amplifier. It starts with arbitrary choice of emitter current, followed by worse arbitrary choice of voltage drop across emitter's resistor, and ends with erroneous calculation of middle point for output AC amplified signal to swing around. Reasoning for this approach is that you are dealing with equation with several unknown variables, so you have to make choices and assumptions, in order to start from somewhere. And to put salt to injury, this is textbook approach, this is what we are served as education. Why on earth would you choose arbitrary current as a starting point for a voltage amplifier? It is misunderstandable. It makes no sense. If you are building current amplifier, okay, that would make sense. You are designing your amplifier to have output current of certain desired value, and that is okay. But you are not building current amplifier, you are building voltage amplifier, output current is irrelevant. Next part of this travesty refers to calculating values for collector and emitter resistor value. The math is displayed on the screen. Also, at this point we have to define amplification parameter of the voltage amplifier. By definition, ratio between collector and emitter resistor is amplification, marked with capital letter A. So, amplification of this amplifier is around 5 times. Okay, let's leave it at that. At later point in this video, we will explain entire stupidity of this 5 times amplification value. Make a mental note for this point in the video. Next, author of this bovine sophistry decides to introduce beta, in order to derive base current. There is also assumption that beta is 100, so base and collector currents are calculated accordingly, based on arbitrarily chosen value for emitter current. One would think, okay, this is fine, beta is always assumed 100 for ease of calculation, no damage there, right? One of the most important features of voltage amplifiers is that they are beta independent. Again, one of the most important features of voltage amplifiers is that they are beta independent. No need to repeat it third time for luck, you got the gist of it. Amplification of voltage amplifier is calculated only and only by ratio of collector and emitter resistors. Beta plays no role whatsoever. Furthermore, if we want to nitpick, beta is wrong parameter for this discussion. What author should be emphasizing is that beta is ratio between collector and base current with no small AC signal present, and that there is another parameter, that measures exactly the same thing, but this time with small AC signal present. The parameter that should have play in this part is HFE. If you do not know difference between beta and HFE, we have several videos dedicated to this topic, so give them a view after you are done with this one. Next in this insanity is the voltage drop across resistors R1 and R2. In order to obey laws of physics, two components in parallel must share the same voltage. This enforces that voltage drop across resistor R2 has to be the same as sum of voltage drop across base emitter junction, and voltage drop across emitter resistor. Consequently, voltage drop across resistor R1 is calculated accordingly. The math is displayed on the screen. Next part is brain damaging. If you have managed to get to this point without any serious brain damage, we applaud you. We ourselves have not been so lucky. Next part is all about solving what is colloquially known as left-hand side of the amplifier circuit. We have to find values for resistors R1 and R2. We find ourselves again in similar situation, we have equation with two unknown variables. We know voltage drops across resistors R1 and R2, but we do not know their values, nor their resistance. So, out of his butt, the author spews another assumption. It says, for base current to be of certain value, the current running through resistor R2 has to be 100 times more than base current. This is verbatim from the author's website. Okay, since we have lost any semblance of normality 20 minutes ago, let's just plug in the numbers and calculate. We don't have strength to deal with this insanity no longer. Out of the but assumption says that current running through resistor R2 is 100 times bigger than base current. Since base current is calculated at 110 microamperes, math says that current running through resistor R2 is 11 milliamperes. Consequently, current running through resistor R1 is sum of base current and current running through resistor R2. Given voltage drops across resistors, and out of the but derived currents, we get values for resistors R1 and R2. They are displayed on the screen. Now, since we are no any ultimate authority, nor we claim to be one, when it comes to the question of NPN transistors and amplifiers, we need objective third party to see if this circuit will actually work. If you have seen our previous videos, you are familiar with the fact that we are no strangers relying on PSpice Simulator, in order to verify the results. But, before we do that, there is just one tiny simple question left unanswered. Page after page of assumptions, and pulling out of but values and approximations, but not a single word about what is it that we are actually amplifying. Surely, there has to be at least sentence about the signal, right? Something about amplitude, point-to-point voltage, frequency, period, at least that stupid sine wave that everyone always draws with amplifier circuit schematics, right? Well, yes there is. There is one, and only one sentence in entire tutorial about the signal. It says, verbatim, small AC input signal ranges between couple of microvolts to couple of millivolts, for Class A amplifiers. So, we are dealing with signals that ranges from 10 to power of -6, to 10 to power of -3, according to this website. Fine, now comes part where everything falls apart. Remember a couple of minutes ago, when we asked you to make a mental note, regarding magnitude of amplification for this particular circuit. According to the instructions, we have calculated that this particular circuit amplifies input signal 5 times. Okay. But, if our signal ranges from 10 to power to -6, all the way to 10 to power to -3, 5 times amplification is negligible. There are some expectations regarding output signal. Are we amplifying it to rise to line audio output level, which is about 1.4 volts peak to peak, or we are amplifying it to drive speakers, so we can actually hear something? In any case, our output signal should be well in volts range, not staying dwarfed in micro or millivolts output range. Designing circuit like this is exercise in futility. If you have signal in microvolts range, and you amplify it 5 times, unless you have some high-precision oscilloscope, that costs arm and a leg, you cannot even observe this amplified output signal on DS0138 oscilloscope, for example. All you see will be a flat line. It simply doesn't have the resolution to display signals in microvolts range. So, even if you do everything correctly, and assemble this circuit on the breadboard, unless you have NASA-type oscilloscope, all you will be able to see is flat line. And while on this subject, please never, but never try to assemble this particular circuit on the breadboard. You will blow entire circuit, and do some pretty good damage to the breadboard, but more about this later. Now, let's get back to our PSpice simulation. We need to check does this circuit actually work, and to check that we did not make any errors tracing back this tutorial. Let's run this circuit in PSpice without any input signal, and see if we got all the currents right. Right on the spot. Everything is pretty much exactly what it should be. Now, to give this abomination of the circuit every possible chance of success, let's go with 20 mV point-to-point small AC input signal. This is maximum what the author suggests for this type of the circuit. You can already guess the output, but, nevertheless, let's run the simulation. Surprise, flat line. Poop. To be fair, let's blow up the output to the maximum. Yes, there is 5 times amplification of input signal, but it is negligible. Output signal swings from 15.75 to 15.85 volts. Wow! If your intent was to amplify signal to hearing level, you will be able to hear absolutely nothing. An entire tutorial is dedicated to A-class audio amplifiers. Great job! The author designed this circuit around 30 volts power supply, which should enable entire signal to swing in at least 26 volts DC domain, but no, the output signal swings in 0.1 volts DC domain. Impressive. Now, remember a couple of minutes ago when we warned you not to try to assemble this circuit on breadboard. It will end badly for few of the components, and breadboard itself. This circuit is dangerous. That is why we opted to debunk this in PSpice simulator, rather than assembling circuit on the breadboard, and observe output on the oscilloscope. And since we do not have NASA-level oscilloscope, but only our beloved DS0138, we wouldn't be able to see pretty much nothing anyway. Now, why is this circuit right down dangerous? Let's deal with maximum ratings for all our components. From previous videos and datasheets, we know that we should never run any electrical component close to its maximum electrical ratings. Best practice suggests that we always run our components at half of the maximum declared ratings, to avoid overheating, and to prolong lifespan of our components. If your supplier of components is Far East Online premium quality top-of-the-line 100 pieces for dollar deals, you are probably dealing with NPN transistor 2N3904, or similar, and quarter-watt resistors. For transistor, maximum heat dissipation is 625 milliwatts, under unrealistic laboratory test conditions. For resistors, it is 125 milliwatts, maximum. For safety purposes we need to halve these values, so we get around 300 milliwatts for transistor, and 60 milliwatts for resistors. These values ensure that there will be no overheating of any component, and circuit will run without any problems for any length of time, requiring no active cooling. Let's get back to our PSpice simulation and run power dissipation simulation. Results are astonishing. Collector resistor RC and resistor R1 are dead on arrival. Both of them are well beyond maximum recommended ratings, so they will overheat and blow up in matter of seconds. Resistors RE and R2 are in safe range, but that doesn't count, since resistors RC and R1 are already blown up. Furthermore, if you let this circuit run to its unceremonious and undignified end, melting resistors will severely damage breadboard at points of contact, rendering that part of breadboard unusable for any further projects. We know this first, second, third hand, and counting. So, this tutorial that we are reacting to and debunking, provided not only unusable and pointless amplifier, but rather dangerous one. Even if you halve the supply voltage, or even more, resistors RC and R1 are always going to blow up. Is there more stupidity to debunk and react to in here? Surprisingly and unfortunately, yes. If we were to try and fix the situation, theory suggests that we change ratio between collector and emitter resistor, so that we get bigger amplification. Since by definition, amplification of the amplifier is ratio between those two resistors, increasing resistance for collector resistor will increase amplification. If we make ratio 100 times, or more, we will get our signal in range of couple of volts point to point. Headphones should be able to reproduce this output in audible range. However, the author did not set values for RC and RE. Instead, he opted to pull current IE out of his butt, and set voltage drop across emitter resistor to 10% of power supply. Everything else is calculated, based on these two assumptions, arbitrary emitter current, and power supply. So, we cannot change collector resistor RC to 100 times bigger value. If we do this, we violate first assumption, that emitter current is 11 milliamperes. Entire calculation goes down the drain. Is there more? Yes. This entire tutorial was pulled out of one of the most visited sites on the internet. The tutorial was there to teach us how to design NPN amplifiers, based on textbook theory, the way it is presented and taught in school. This entire travesty is how we teach our pupils and students about amplifiers. Unless you have been away on Mars for last couple of years, and missed development of large language models, and emergence of what we are told to call artificial intelligence, you are in for a real treat. Large language models, and consequently all emerging AI models, are trained on content of most popular and most visited sites on the internet. Now, this entire site, and this particular tutorial were one of the primary sources for development of LLM's portion dedicated to electronics. If you ask any of AI models any electronics question, this particular site is always primary source of slop that AI model hallucinate out as an answer. Unspeakable travesty. Unbelievably, but things are even worse. We are yet to find any written or video tutorial that is not based on this right down stupid and dangerous travesty, set as standard on how to design and calculate values for NPN transistor-based amplifiers. If you were like we were once, trying to learn about electronics based on tutorials from this or similar sites, and found them incomprehensive and erroneous, we hope that that experience did not demoralize you to continue to learn about electronics. When taught the right way, electronics is easy and lots of fun, so one way to enjoy learning about electronics in fun and productive way is to subscribe to our channel. We promise to teach you how to design bulletproof NPN amplifier, with full input range, and variable output range, with no assumptions. As we have already said, electronics is a lot of fun. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to our channel. Thank you, and bye.